Welcome back, student. So, in our last class, if you remember, we show some polynomial which we call Legendre polynomials. The significance of these polynomials is this is P0x was, let me write it here, P0x was 1, P1x was x, P2x was half 3x square minus 1. It is something like this. There was a generating function that we also mentioned. If I want to find out what is the value of Pn, then it should be essentially 1 by factorial 2 to the power n factorial n, then d2 dx square x square minus 1, something like that. The thing is that these polynomials are forming a orthogonal set. So, how many orthogonal set we find? Let me write it here once again. So, that the very first and fundamental was 1x x square this. These are say in the range minus 1 to 1. These were linearly independent set of function. They are not orthogonal. If you calculate the orthogonality, you will find that, for example, if I try to find out the inner product of 1 and x square, it should be something like minus 1 to 1, 1 into x square dx. It should be x cube by 3 minus 1 to 1. It will come up as 2 divided by 3, which is not equal to 0. 1 is a function and x square is a function. I just take these two functions and then try to find out what is the inner product between these two. If the inner product is any of this linearly independent set of function, if the inner product is 0, then we can say they are orthogonal to each other, but here we find that it is not equal to 0, they are not orthogonal, but they are linearly independent. If you calculate the Wronskian, you can readily figure it out. So, this is one kind of linearly independent set, and you can expand a function in terms of this. Another was one sin x cos x sin 2x cos 2x and so on in minus pi to pi, this limit, this range. So, this set of function are also linearly independent and they are also linearly independent and orthogonal. That means, if you take the integration over this limit, you will find that they are going to vanish. So, also they are potentially form the basis. So, here is a set of function which can form a basis. Here is a set of function which can form a basis. If you remember, the Fourier series is based on this basis. So, the Fourier series, any function, if I want to expand in terms of Fourier series, we are going to use this basis. Next, we find another last day, which is nothing but the Legendre polynomials. Potentially, they are also form a set which are linearly independent and orthogonal. If they are linearly independent and orthogonal, they are also can be used as a basis function, and if I expand this function in terms of in some coefficient, I can regenerate whatever the function I want. So, that means they are forming a basis function. So, there are 3 different kind of basis function that we have. Also, if you remember, let me erase that, the middle one that we have already used in the Fourier series, and we know how to deal with that. But from here to here in the last day, we calculate that if a set of linearly independent function is given to you, how to make this linear independent set of function a set of orthogonal function or orthonormal function. If I put the normalization constant here, then it should be normalized also, and we use the standard Gram-Schmidt method. Gram-Schmidt method of orthonormalization. But please remember that when you make the Gram-Schmidt orthonormalization method, then we put our inner product formalism as phi I phi j is equal to integration of some limit, say a to b phi I phi j dx, if both the function is dx. If you remember another thing, that this definition we put by making the weight function, if I say w is my weight function, is 1, or we define that in terms of r is 1. So, crude reference, I mean crude, if I try to write it more general way, critical way, then it should be something like phi j and r dx. R was the density function or the weight function, whatever you say. But if I put r equal to 1, then my inner product definition will come to this, and because of that I come across this linearly independent set of function, if you remember. But someone can change this thing by putting some value of r, some function of r, whatever. If they put some value of r, then readily you can understand that this definition will going to change, inner product definition will going to change because of this weight function or the density function r, and you are start getting a different kind of or set of functions, which not be essentially the Legendre polynomials. It would be some different kind of polynomial, but still we are in a position to find a set of orthogonal function which is not in this form. It may be different, it may be Hermite polynomial, there are different kind of polynomial, Laguerre polynomial. This polynomial are also behave like a linearly independent set of functions, but here we put a specific example which is the Legendre polynomial, and we find that it can be derived directly from this basis to another basis by using the Gram-Schmidt method. By the way, at this point I should mention that there is a name of this basis, we normally call it monomial basis. So, this from monomial basis I can generate my a set of functions which are Legendre polynomials essentially. Now, as I mentioned, a function, let me try to do something, some example, for example, some problem, for example. So, a function, make it, I try to make it general. So, say a0 plus a1x plus a2x plus a2x square plus say a3 x cube, something like this. So, this function is defined in terms of monomial basis. Why? Because this is the coefficient, this is the coefficients, some real numbers or coefficients, and these are the basis function. Now, the question is, I can write this thing in terms of the other basis also. For example, the same function, it is exactly like a vector. If you, let me write it here, the vector form. If a vector v is given to you, you can write this vector say V I E I in this basis, and also you can write this with another basis which is prime basis. This is a natural basis. Normally we put this notation for natural basis. This is another kind of basis which called a prime basis, but the same function I can write it here, and we know that if I write it in this form, then there is a relationship between these and these. Here also we are trying to do the similar kind of thing. That means I am writing a function in terms of monomial basis, and it is possible to write this as like this, and so on. I can extend the term up to my my liking. So, that means a function is represented in terms of this basis which is 1 x n, and then we can expand the same function in another basis which is this. Now, the question is, now if you, this is also some real numbers. Now, the question is, if this is a real number, then this real number should not be same as this real number may not be same as this real number may not be same as this. So, A and B are somehow related, but they are not equal. If they are equal, then this has to be same. We also proved that in our previous class. In one particular basis, the function or a vector can be expressed uniquely for that particular basis. Uniquely means this value should be unique for that, it not going to change every time for fixed basis, but if I change the basis, this coefficient will going to change. So, that means now I need to write some different notation. Here if I write A0, I need to write B0, B1 and so on. Now, I mean you can readily find out what is the relation between these two. So, now I write explicitly, and let us take for up to this, say some function is given like this, and you are asked to write it and try to find out, you are asked to find out what is the relationship between A0, A1 and A2 with this quantity. How to do that? Quite simple. In fact, you can, I believe all of you have already readily, I mean find what should be the, readily in your mind the scheme is there. So, how to do that? So, I will just expand this P0. So, here P01 is 1. So, it is B0, B1 it is x, no problem with that, B2 is P2, P2 is defined as this. If I expand the same function in terms of my given basis, which is the Legendre polynomial, I will have these things. Now, if I slightly rearrange these things, I should write, because there is a B2 half multiplied by this plus B1 x plus 3 by 2 B2 x square. Now, you can readily find that this quantity and this quantity is written in the form of monomial basis. This is of order 1, this is x and this is x square, exactly the way it is given. So, that means essentially this is equal to A0, this is equal to A1 and this is equal to A2. So, there is a straight way that there is a relationship between this quantity. So, A0 will be B0 minus half B2, A1 will be B1 and A2 will be 3 by 2 B2. A1 you know, A2 you know, which is B1 and B2. When B1 and B2 is given to you, A0 is known to you. So, B0 you can find out, because now you know what is your B2, and you replace this and you can readily figure out what is the relationship between the coefficient of monomial basis and the coefficient of your Legendre polynomial basis. So, let us do a very simple problem. So, let me write somewhere the relation. I will going to use that, or I can directly do that. Quickly, so say 1 plus 2x minus 3x square. If a polynomial is given to me, now we are asked to find out. So, what is my a0 here? 1. What is my a1 here? 2. What is my a2 here? Minus 3. If these values are given, then I would like to write it as b0 into 1 plus b1 into x plus b2 into half 3x square minus 1. I can write it in terms of my Legendre polynomials. Then quickly, b0 minus b2 by 2 is here, plus b1 is here, plus 3 by 2 b2 x square is here. Exactly the same way I did just few minutes ago. So, this value is how much? This value is a0, which is equal to 1. This value I readily figure out, this is a1, which is 2, and this value is a3, which is minus 3. So, that means I have an equation b0 minus b2 by 2 is equal to 1, b1 is 2, readily I find, and 3 by 2 b2 is equal to minus of 3. So, b2 from here I figure out it should be minus 2. So, I know what is my b2, which is minus 2. I know what is my b1, which is 2. I need to find out b0. So, b0 is 1 plus b2 by 2. b2 I already figure out here, which seems to be okay. Let me check once again if I am doing something wrong here or not. b2 is minus 2. If it is minus 2, then b0 comes out to be 0. Okay, maybe let us, I will check that. So, it seems to be b2 is minus 2. If I put minus 2, then 1 minus 1 0. So, b0 is come out to be 0. So, let me write somewhere here what value I am getting, and then put that and check whether it is coming or not. So, my b0 is 0, b1 is 2, and b2 is minus 2. Now, if I put this here, then you can readily find out. If I put this value, then it will be 0 plus p1 is 2, it is 2x minus 3x square minus 1. So, this quantity is same. So, if this is the coefficient for monomial basis, the coefficient for Legendre basis, Legendre polynomial basis is this. It is writing it is same thing like writing one vector and changing that vector to another basis, same vector that the coefficient is going to change. Mind it, here it is 1 2 3, now it is 0, come to 0 2 minus 2. Now at this point I would like to mention something quite interesting, that if a polynomial is given to you, let me erase this. With this also I do not need to write this or either this, let me erase. For example, a polynomial is given to you, nth order polynomial, I write it as Pn, which is a0 plus a1 x plus a2 x square plus a n x to the power n. This is a polynomial given to you. Once the polynomial is given to you, you can readily have a mapping. What kind of mapping? That I will, this is the T which is the mapping, T will do what? Pnx polynomial, it will transfer, T is some kind of mapping which transfer, let me write it in this way, which transfer a nth order polynomial to a vector of order n plus 1. How? If I have a polynomial like this, a0 plus a1 x plus a2 x square plus a n x to the power n, then this transformation or mapping suggests that from that polynomial I can make a vector which contain only this coefficient, this coefficient, this coefficient, this coefficient. So, if I write this coefficient, I will have a vector, of dimension n plus 1. So, from a nth order polynomial I can make a vector, this vector is nothing but the coefficient is the coefficient that is given to you. I write this coefficient in a column vector, and when I write this column vector I can have direct mapping from this polynomial to a vector. This sometimes called is isomorphism. This is a technical term that for a given any given polynomial I can write this polynomial in terms of a vector with this mapping. For example, the example is straightforward and quite simple, even I think you have already understand what is the meaning of these things. So, say a polynomial is given like 1 plus 3x minus 4x cube minus 5x4 plus 6x to the power 7, something like this. So, you can find that there are few terms, few order that is missing. So, I can write this as 1 plus 3x plus 0 into x square minus 4 into x cube plus minus 5 x to the power 4 plus 0 x to the power 5 plus 0 x to the power 6 plus 6 x to the power 7. So, the order of this polynomial is 7, n value is 7. If the order is 7, then I can form with the mapping T mapping a vector of this form 1 3 0 minus 4 minus 5 0 0 6. This will be my corresponding vector, quite simple. And if you find what is the dimension 1 2 3 4 5 6 7 8. So, it should be n plus 1 dimension, which is 8. Now, another important thing in this polynomial, let me do that. For example, I have a polynomial f(x) is equal to a0 plus a1x plus a2x square plus a3x cube. If I have this polynomial, then if I translate that, that means from x point I should add something here which is called translation, then in the right hand side something will change and I have some expression like this. Once I have some expression like this, then if I rearrange these things, so let me write it once again, a1 then a1 x plus c, then a2 x square plus 2 x c plus c square plus a3 x cube plus 3 x square c plus 3 x c square plus c cube. Now, if I rearrange the term, then I will have a0 plus a1 c plus a2 c square plus a3 c cube. The first term I am rearranging these things plus second term a1 all the coefficient with respect to x plus 2 a2 c, then plus 3 a3 c square x. The next one is all the coefficient with square, a2 there is a square plus a3 into 3c, this quantity into square. Hope I am not missing anything. And finally the cube, this is a3, just a3. So, even though I am changing these things, so this is a new coefficient. So, if I write this in terms of new coefficient, it will be b0 plus b1 x plus b2 x square, I should write x cube here, plus b3 x cube. This was the basis. This is another the same thing I am writing, but with a translation. Now, these things b0, b1, b2, b3, if you find, if I check carefully, then what is my b0? b0 is nothing but f of c. If I put this quantity in place of x, if I put c, then I will have fc. What is my b1? b1 is the derivative. If I make a derivative and then if I put c on that, then I will have these things. So, if I make a derivative, this quantity is not be there, it will be a1, then it will be 2 a2 c, and it will be 3 a3 c square, So, this quantity is the derivative of this quantity. What will be my b2? b2 is the double derivative of c with respect to 2 divided by factorial 2. If I make a double derivative, this quantity will not be there, this quantity will not be there. Here will be 2 a2, I have a2 here I have a3. So, if I make a double derivative, it will be 3 into 2, 6 a3 x. So, I will have 3. So, if I make it divided by 2, then it will be 3. So, I will have this quantity. And finally, I want you to check, please check if it is really coming or not. it will be something like this. I believe you now start remembering what is the this so called Taylor series. So, it is nothing but the Taylor series expansion with this. Another important thing is that if I put C equal to 0, then Fc, then Fx with put C equal to 0, I can also write in this form. I put a factorial 1 here to make it more convenient. Factorial 1 is 1, so I should not bother about this. And finally, this and this, if you check this and this, there is a different basis I can form. You can see this basis is slightly different from the previous one. This is a monomial basis. I am writing the same function, but this basis is slightly changed. This basis is called factorial basis. So, I can write the same function in terms of monomial basis, I can write the same function in terms of factorial basis. So, now if a function is given to you, then you can understand how to change this from monomial basis to factorial basis. A quick example, I will not do this problem entirely, it will be used as a homework, but very simple. So, Fx for example 1 plus 2x minus 3x square. So, what is the, if I make it t mapping over that, what will be the vector form? The vector form is 1, 2 and minus 3 straightway. Now, the question will be, if I write this Fx in terms of factorial basis, it should be written in the form like f0 plus f prime 0 x factorial 1 and plus f double prime 0 x square factorial 2. So, this is what is the basis here, 1 x square, this is monomial basis. Now, you can write this function in this way, make a transformation, just put this value here f0, f prime 0 and f double prime 0, you will have a different value. This will be for the basis 1 x square with this basis. So, I can write this is monomial basis as well as my factorial basis. Since the function is given to you, we can readily understand what will be your f0, what will be your f prime 0 and what will be your f double prime. This is double prime, by the way, double prime 0. So, then you can, whatever the problem is given to you, you can write this function with the transformation with this basis or this basis according to your choice. Okay, students, so this is the last part of the linear vector space. So, I am going to stop here, and in the next class maybe I will going to start a new topic, which is the complex analysis, a very important one. So, with that let us conclude here. Hope you enjoy this linear vector space, the different aspects of linear vector space, and now you have a better idea of how to do dealing with these things and from where it is coming. Everything is related to the function and vector is related to this linear vector space concept, the inner product and all these things, which are very important concept. So, now I think your understanding will be more better when you deal with this kind of problems. So, with this hope, let us conclude here. To see you in the next class. Thank you.